This episode is brought to you by Cisco Educational Premium. Did you know that Planck units are units of measurement? In particle physics and physical cosmology, Planck units are a set of units of measurement defined exclusively in terms of four universal physical constants, in such a manner that these physical constants take on the numerical value of 1 when expressed in terms of these units. Originally proposed in 1809 by German physicist Max Planck. These units are a system of natural units because their definition is based on properties of nature, more specifically the properties of free space, rather than a choice of prototype object. They are relevant in research on unified theories such as quantum gravity. The term Planck scale refers to quantities of space-time energy and other units that are similar in magnitude to corresponding Planck units. This region may be characterized by particle energies of around 10 raised to 19 gigavolts or 10 raised to 9 joules. Time intervals of around 10 raised to negative 43 seconds and lengths of around 10 raised to negative 35 meters, approximately the energy equivalent of the Planck mass, the Planck time, and the Planck length respectively. At the Planck scale, the predictions of the standard model, quantum field theory, and general relativity are not expected to apply, and quantum effects of gravity are expected to dominate. The best known example is represented by the condition in the first 10 raised to negative 43 seconds of our universe after the Big Bang, approximately 13.8 billion years ago. The four universal constants that by definition have a numerical value of 1 when expressed in these units are 1. The speed of light in a vacuum c. 2. The gravitational constant g. 3. The reduced Planck constant h. And 4. The Boltzmann constant k sub b. Planck units do not incorporate an electromagnetic dimension. Some authors choose to extend the system to electromagnetism by, for example, adding either the Coulomb constant k sub e is equivalent to 1 on 4 pi E naught or electric constant E naught to this list. Similarly, authors choose to use variants of the system that give other numerical values to one or more of the four constants we have seen. Any system of measurement may be assigned a mutually independent set of base quantities and associated base units, from which all other quantities and units may be derived. In the International System of Units, for example, the SI base quantities include length with associated unit of the meter. In the system of Planck units, a similar set of base quantities and associated units may be selected, in terms of which other quantities and coherent units may be expressed. The Planck unit of length has become known as the Planck length, and the Planck unit of time is known as Planck time, but this nomenclature has not been established as extending to all quantities. All Planck units are derived from the dimensional universal physical constant that define the system, and in a convention in which these units are omitted, that is treated as having dimensionless value 1. These constants are then eliminated from equations of physics in which they appear. For example, Newton's law of universal gravitation. Of course, these Planck constants appear, so they are eliminated as shown by the second equation. Both equations are dimensionally consistent and equally valid in any system of quantities, but the second equation with g absent is relating only dimensionless quantities, since any ratio of two like dimensioned quantities is a dimensionless quantity. If By shorthand convention, it is understood that each physical quantity is the corresponding ratio with a coherent Planck unit, or an quote expressed in Planck units. The ratios we have seen may be expressed simply with the symbols of physical quantity without being scaled explicitly by their corresponding unit. This last equation without G is valid with F prime, M1 prime, M2 prime, and R prime, being the dimensionless ratio quantities corresponding to the standard quantities written, for example, F prime being F or F prime being F1, Fp, but not as a direct equality of quantities. This may seem to be like what setting the constant Cg etc. to 1 if the correspondence of the quantities is thought of as equality. For this reason, Planck or other natural units should be employed with care, referring G is equivalent to C is equivalent to 1. Paul S. Wesson wrote that mathematically it is an acceptable trick which saves labor. Physically, it represents a loss of information and can lead to confusion. The concept of natural units was introduced in 1874 when George Johnston Stoney noted that electric charge is quantized. Derived units of length, time, and mass now named Stoney units in his honor. Stoney chose these units so that G, C, and the electron charge E would be numerically equal to 1. In 1899, 1 year before the advent of quantum theory, Max Planck introduced what became later known as Planck constant. At the end of the paper, he proposed the base units that were later named in his honor. The Planck units are based on the quantum of action, now usually known as the Planck constant, which appear in the Wien approximation for black body radiation. Planck underlined the universality of the new unit system, writing, "It is possible to set up units for length, mass, time, and temperature, which are independent of special bodies or substances, necessarily retaining their meaning for all times and for all civilizations, including extraterrestrial and human ones, which can be called natural units of measure." Planck considered only the units based on the universal constants GH, C, and KB to arrive at natural units for length, time, mass, and temperature. These definitions differ from the modern ones by a factor of √2 pi because the modern definitions use reduced Planck's constant rather than Planck constant. Unlike the case with the International System of Units, there is no official entity that establishes a definition of a Planck unit system. Some authors define the base Planck units to be those of mass, length, and time, regarding an additional unit for temperature to be redundant. Other tabulations add, in addition to a unit of temperature, a unit for electric charge, so that either the Coulomb constant Ke or the vacuum permittivity E0 is normalized to 1. Thus, depending on the author's choice, this charge unit is given. Some of these tabulations also replace mass with energy when doing so. The Planck charge, as well as other electromagnetic units that can be defined like resistance and magnetic flux, are more difficult to interpret than Planck's original units and are used less frequently. In SI units, the values of CH, E, and KB are exact, and the values of E0 and G in SI units respectively have relative uncertainties of 1.5 times 10 raised to negative 10 and 2.2 times 10 raised to negative 5. Hence, the uncertainties in the SI values of the Planck units derive almost entirely from uncertainty in the SI value of G. Compared to the Stoney units, the Planck base units are all 1 on root alpha, approximately 11.7 times larger. In any system of measurement, Units for many physical quantities can be derived from base units. The table has a sample of derived Planck units, some of which are seldom used. As with the base units, their use is mostly confined to theoretical physics because most of them are too large or too small for empirical or practical use, and there are large uncertainties in their values. Some Planck units, such as those of time and length, are many orders of magnitude too large or too small to be of practical use. So that Planck units as a system are typically only relevant to theoretical physics. In some cases, a Planck unit may suggest a limit to a range of physical quantity where present-day theories of physics apply. For example, our understanding of the Big Bang does not extend to the Planck epoch, that is, when the universe was less than 1 Planck time old. Describing the universe using the Planck epoch requires a theory of quantum gravity that will incorporate quantum effects into general relativity. Such a theory does not yet exist. Several quantities are not, and I quote, extreme in magnitude, such as the Planck mass, which is about 22 micrograms, very large in comparison with subatomic particles and within the mass range of living organisms. Similarly, the related units of energy and momentum are in the range of some everyday phenomena. Planck units have little anthropocentric arbitrariness, but do still involve some arbitrary choices in terms of the defining constants. Unlike the meter and second, which exist as base units in the SI system for historical reasons, the Planck length and Planck time are conceptually linked at a fundamental physical level. Consequently, natural units help physicists to reframe questions. Frank Wilczek puts it succinctly. We see that the question is not why is gravity so feeble, but rather why is the proton's mass so small? For in natural Planck units, the strength of gravity simply is what it is, a primary quantity, while proton's mass is the tiny number 1 on 13 quintillion. While it is true that the electrostatic repulsive force between two protons alone in free space greatly exceeds the gravitational attractive forces between the same two protons, that's not about the relative strength of the two fundamental forces. From the point of view of Planck units, this is comparing apples with oranges because mass and electric charge are incommensurable quantities. Rather, the disparity of magnitude of force is a manifestation of the fact that the charge on the proton is approximately the unit charge, but the mass of the protons is far less than the unit mass. In particle physics and physical cosmology, the Planck scale is an energy scale around 1.22 times 10 raised to 19 gigafolds. The Planck energy corresponding with the energy equivalent of the Planck mass is 2.17645 times 10 raised to negative 8 kilogram, at which quantum effects of gravity become significant. At this scale, present description and theories of subatomic particle interactions in terms of quantum field theory break down and become inadequate due to the impact of the apparent non-renormalization of gravity within current theories. At the Planck scale, the strength of gravity is expected to become comparable with the other forces, and it has been theorized that all the fundamental forces are unified at that scale. But the exact mechanism of this unification remains unknown. The Planck scale is therefore the point at which the effects of quantum gravity can no longer be ignored in other fundamental interactions, where current calculations and approaches begin to break down and a means to take account of its impact is necessary. On these grounds, it has been speculated that it may be an appropriate lower limit at which a black hole could be formed by collapse. While physicists have a fairly good understanding of the other fundamental interactions of forces on the quantum level, Gravity is problematic and cannot be integrated with quantum mechanics at very high energies using the usual framework of the quantum field theory. At lesser energy levels, it is usually ignored, while for energies approaching or exceeding the Planck scale, a new theory of quantum gravity is necessary. Approaches to this problem include string theory and M theory, loop quantum gravity, non-commutative geometry, and causal theory. In Big Bang cosmology, the Planck epoch or the Planck era is the earliest stage of the Big Bang before the time passed was equal to the Planck time, or approximately 10 raised to negative 43 seconds. There is no current available physical theory to describe such short times, and it is not clear in what sense the concept of time is meaningful for values smaller than the Planck time. It is generally assumed that quantum effects of gravity dominate physical interactions at this time scale. At this scale, the unified force of the standard model is assumed to be unified with gravitation. Immeasurably hot and dense, the state of the Planck epoch was succeeded by the grand unification epoch, where gravitation is separated from the unified force of the standard model, in turn followed by inflationary epoch, which ended after about 10 raised to negative 2 seconds, or about 10 raised to 11 Planck time. After the measurement of the cosmological constant in 1998, estimated at 10 raised to negative 122 in Planck units, it was noted that this is suggestively close to the reciprocal of the age of the universe squared. Barrow and Shaw propose a modified theory in which the cosmological constant lambda is a field evolving in such a way that its value remains lambda equivalent to the age of the universe squared through the history of the universe. The Planck length, denoted Lp, is a unit of length defined as Lp is equivalent to root of reduced Planck constant G on C raised to 3. It is equal to 1.61625518 times 10 raised to negative 45 meters, where the two digits enclosed by parentheses are estimated standard error associated with the reported numerical value, or about 10 raised to negative 20 times the diameter of a proton. It can be motivated in various ways, such as considering a particle whose reduced Compton wavelength is comparable to its Schwarzschild radius. Though whether those concepts are in fact simultaneously applicable is open to debate. The same heuristic argument simultaneously motivates the Planck mass. The Planck length is a distance scale of interest in speculation about quantum gravity. The Bekenstein-Hawking entropy of a black hole is 1/4 area of its event horizon in units of Planck length squared. Since 1950s, it has been conjectured that quantum fluctuations of the space-time metric might make the familiar notion of distance inapplicable below the Planck length. This is sometimes expressed by saying that, and I quote, space-time becomes a form at the Planck scale. It is possible that the Planck length is the shortest physically measurable distance, since any attempt to investigate the possible existence of shorter distances by performing high-energy collision will result in a black hole production. High-energy collision, rather than splitting matter into finer pieces, would simply produce bigger black holes. The strings of string theory are modeled to be on the order of the Planck length. In theories with large extra dimensions, the Planck length calculated from the observed value of G can be smaller than the true fundamental Planck length. The Planck time, Tp, is the time required for light to travel a distance of 1 Planck length in a vacuum, which is a time interval of approximately 5.39 times 10 raised to negative 44 seconds. No current physical theory can describe time scale shorter than the Planck time, such as the earliest events after the Big Bang. Some conjecture that the structure of time need not remain smooth at intervals comparable to the Planck time. The Planck energy EP is approximately equal to the energy released in the combustion of the fuel in automobile fuel tank, 57.2 liters at that 4.2 megajoule per liter of chemical energy. The ultra energy cosmic ray observed in 1991 had a measured energy of about 50 joules, equivalent to about 2.5 times 10 raised to negative 8 Planck energy. Proposal for theories of doubly special relativity posit that in addition to the speed of light, an energy scale is also invariant for all inertial observers. Typically, this energy scale is chosen to be the Planck energy. The Planck unit of force may be thought as the derived unit of force in the Planck system if the Planck units of time, length, and mass are considered to be the base units. It is the gravitational attractive force of two bodies of one Planck mass each that are held one Planck length apart. One convention for the Planck charge is to choose it so that the electrostatic repulsion of two objects with Planck charge and mass that are held one Planck length apart balances the Newtonian attraction between them. Some others have argued that Planck force is on the order of the maximum force that occurs between two bodies. However, the validity of these conjectures has been disputed. The Planck temperature Tp is 1.41678416 times 10 raised to 32 Kelvin. At this temperature, the wavelength of light emitted by thermal radiation reaches the Planck length. There are no known physical models able to describe temperatures greater than the Planck temperature. A quantum theory of gravity would be required to model the extreme energies attained. Hypothetically, a system in thermal equilibrium at the Planck temperature might contain Planck scale black holes, constantly being formed from thermal radiation and decay via Hawking evaporation. Adding energy to such a system might decrease its temperature by creating larger black holes whose Hawking temperature is lower. Physical quantities that have different dimensions such as time and length cannot be equated even if they are numerically equal. Like 1 second is not the same as 1 meter. In theoretical physics, however, this problem may be set aside by a process called non-dimensionalization. The effective result is that many fundamental equations of physics, which often include the sum of the constants used to define Planck units, become equations where these constants are replaced by 1. Examples include the energy momentum relation becomes E square is equivalent to C square bracket all of that raised to 2 plus PC square, which become E square is equivalent to M square plus P square. And the Dirac equation, which evolved, which becomes as shown. As we have already looked at, Planck units are derived by normalizing the numerical values of certain fundamental constants to 1. These normalizations are neither the only ones possible nor necessarily the best. However, the choice of what factors to normalize among the factors appearing in the fundamental equation of physics is not evident, and the values of Planck units are sensitive to this choice. The factor 4 pi is ubiquitous in theoretical physics because in three-dimensional space, the surface area of a sphere of radius r is 4 pi r square. This, along with the concept of flux, are the basis for the inverse square law, Gauss law, and the divergence operator applied to the flux density. For example, gravitational and electrostatic fields produced by point objects have spherical symmetry, and so the electric flux through a sphere of radius r around a point charge will be distributed uniformly over that sphere. For this, it follows that a factor of 4 pi r square will appear in the denominator of Coulomb's law in rationalized form. Both the numerical factor and the power of the dependence on R would change if space were higher dimensional. The correct expression can be deduced from the geometry of higher dimensional spheres. Likewise, for Newton's law of universal gravitation, a factor of 4 pi naturally appears in Poisson's equation, one relating the gravitational potential to the distribution of matter. Hence, a substantial body of physical theory developed since Planck's 1899 paper suggests normalizing not g but 4 pi g or 8 pi g to 1. Doing so introduced a factor of 1 on 4 pi or 1 on 8 pi into non-dimensionalized form of the law of universal gravitation, consistent with the modern rationalized formulation of Coulomb's law in terms of vacuum permittivity. In fact, alternative normalizations frequently preserve the factor of 1 on 4 pi in the non-dimensionalized form of Coulomb's law as well, so that the non-dimensionalized Maxwell's equation for electromagnetism and gravitoelectromagnetism both take the same form as those for electromagnetism in SI, which do not have any factors of 4 pi. When these apply to electromagnetic constants, E naught, this unit system is called, and I quote, rationalized. When applied additionally to gravitation and Planck units, these are called rationalized Planck units and are seen in high energy physics. The rationalized Planck units are defined so that C is equivalent to 4 pi g, which is equivalent to reduced Planck's constant, which is equivalent to E naught, which is equivalent to KB, which is equivalent to 1. There are several possible alternative normalizations. In 1899, the Newton's law of gravitation was still seen as exact, rather than as a convenient approximation holding for and accord small velocities and masses. The approximate nature of Newton's law was shown following the development of general relativity in 1915. Hence, Planck normalized 1 the gravitational constant g in Newton's law. In theories emerging after 1899, g nearly always appears in formulae multiplied by 4 pi or a small integer multiplied thereof. Hence, a choice to be made when designing a system of natural units in which, if any, instances of 4 pi appearing in the equations of physics are to be eliminated for the normalization. 1. Normalizing 4 pi g to 1 and therefore setting g to be equivalent to 1 on 4 pi. Whose law for gravity becomes phi g, which is equivalent to negative 4 pi m in Planck units. Something else is that it eliminates 4 pi g from the Poisson equation. Also, it eliminates 4 pi g in the gravitoelectromagnetic GM equation, which hold in weak gravitational fields or locally flat spacetime. These equations have the same form as Maxwell's equations and the Lorentz force equation of electromagnetism, with mass density replacing charge density and with 1 on 4 pi g replacing epsilon naught. It normalizes the characteristic impedance Zg of gravitational radiation in free space to 1, normally expressed as 4 pi g on C. It also eliminates 4 pi g from the Bekenstein-Hawking formula for entropy of a black hole in terms of its mass, mbh, and the area of its event horizon, abh, which is simplified to SBH is equivalent to pi, abh is equivalent to mbh square. 2. Setting 8 pi g to be equivalent to 1, and therefore setting g to be equivalent to 1 on 8 pi. This would eliminate 8 pi g from the Einstein field equations, Einstein-Hilbert action, and the Friedmann equation for gravitation. Planck units modified so that 8 pi g will be equivalent to 1 are known as reduced Planck units because the Planck mass is divided by root 8 pi. Also, the Bekenstein-Hawking formula for the entropy of a black hole simplified to C-square educational premium is a section of C-square educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.